work through a real use case analysis using the Constellab Bioprocess Dashboard. The dataset is inspired by a published study on Lactobacillus by Tovilla-Coutino and colleagues in 2022. The original study investigates how fermentation, pH, temperature, and harvest time affect cell growth and the functional properties of the bacteria after freezing or freeze-drying, which matters a lot for industrial starter cultures. For this demo, we simulated the design of experiments dataset inspired by that study. We tested 6 cultures, media, M1 through M6, varying in 4 components. The first one is dipotassium phosphate, the second one is magnesium sulfate, the third one is manganese sulfate, and the last one is ammonium citrate. The rest of the base composition, peptone, glucose, yeast, extract, and so on, is identical across all 6 media. Each medium was replicating 20 times, giving us 120 samples. Growth kinetics were simulating using a logistic for parameter models with growth rates and final yields intentionally designed to differ between media, so we can verify that the dashboard correctly identifies which conditions lead to the best growth. Before we open the dashboard, let me tell you what we built into the data so you can watch the analysis, confirm it step by step. Medium 3, which has the highest dipotassium phosphate at 3 grams per liter and the highest magnesium sulfate at 0.3 grams per liter and citrate at only 1 gram per liter, was designed to produce the fastest growth rate and the highest final OD. At the other hand, M6 with the lowest dipotassium phosphate at 1 gram per liter and citrate at 3 grams per liter were designed to be the worst, producing the slowest growth and the lowest final OD. An interesting case is M4. It has the same high dipotassium phosphate as M3, but its citrate concentration is also 3 grams per liter. The result is that M4 performs no better than M1 or M2. The high citrates has completely cancelled out the benefits of high phosphates. The key hypotheses are higher phosphate and magnesium concentration have positive effect on growth, and citrate has a negative effect. Let's see if the dashboard recovers all of this. We created a recipe using the full input files generated from the simulation. If you would like more information on how to do it, please check the documentation on community or watch the general video about Constellab Bioprocess. So we open the recipe and the Venn diagram shows full coverage. All 120 samples appear in all 3 data sources: info, raw data, and follow-up. No missing samples. We're off to a good start. On the overview page, we can see the summary. 120 samples, 6 media, and 6 batches. We move to the selection step. We will include all 120 samples, no exclusion at this stage, and click to validate. Let's quickly look at the graph view. Here we plot the mean value for each batch of OD over time, colored by batch and therefore by medium here. Immediately you can see a separation. The M3 curves reach the highest plateau around 2 and rise steeply. M6 curves are at the bottom, barely reaching 1.3 grams per liter and have a noticeably slower rise. The striking observation is M4 in purple. Despite having 3 grams per liter of dipotassium phosphate, identical to M3, its curves are flat and low, similar to M1, M2, and M5. This visual already hints that something is suppressing growth in M4 despite the high phosphate. We will confirm this with the analysis. For the quality check, we define a few basic rules. OD must stay between 0 and 3. All samples pass the quality check. This is expected for clean simulated data, but in a real experiment, this step will typically flag samples from fermenters that had sensor failure or contamination events, for example. After the quality check, the analysis section is unlocked. Let's go through each analysis. The first analysis is Medium PCA, a principal component analysis on the medium composition alone before looking at any growth data. The PCA scatter plot shows the 6 media projected into 2 principal components. The first component, PC1, captures most of the variance. The B-plot immediately tells us which nutriments are driving the difference between media and in which direction. PC1 is a contrast between ammonium citrate, whose arrow points to the left, and manganese sulfate, whose arrow points to the right. In other words, PC1 separates media with high citrate from media with high manganese. PC2 is driven almost by dipotassium phosphate and magnesium sulfate, whose arrow points straight upward. Notice that all the constant columns, peptone, glucose, and so on, are collapsed into a single point at the origin with no arrow length. This confirms our media design is clean. Only the intended variables carry information. Now look at where each medium lands. M3 is in the top right. High dipotassium phosphate, high magnesium sulfate, and high manganese sulfate, and above all, low citrate. The combination we designed to give the best growth. M4 is in the left. It has the same height magnesium sulfate as M3, but it's pulled out to the left by its high citrate. Now let's extract growth features. We run feature extraction on OD time series using the logistic 4 parameters model, the same model used to simulate the data, which means we expect an excellent fit. The result table shows some parameters per sample. Looking at the parameter distribution by medium, M3 is a clear winner because it's where param A, the maximum biomass, is higher, and M6 is the worst. We found the same conclusion for paramu, the growth rate. The fitted curves overlay the raw biomass measurement almost perfectly with height R squares values for all samples. With the growth feature extracted, we run metadata feature UMAP. The UMAP plot shows some cluster. The 20 replicates of each medium are grouped together, confirming that medium composition is the dominant source of variation. Their arrangement is meaningful. M3 is isolated in its own corner, and M6 is in the opposite corner. M4 cluster in purple close to M1 and M2, and are not close to M3, despite sharing its potassium phosphate level with M3. The algorithm is picking up the combined effect of medium composition and growth features, and the high citrate of M4 dominates its position in the embedding. This kind of visualization immediately communicates the data structure to someone unfamiliar with the experiment. If you want to find the best medium, look at where M3 sits and understand what makes it different from the rest. One compositional factor, citrates, appear to be pulling performance down. Now let's move to PLS regression, where we train a supervised model to predict the growth parameters from the medium composition. We set the target columns to param A and param mu. The model achieves a R-square above 0.19 on the test state for both targets. It's a strong predictive performance. The VIP score plot is a key result here. It shows that dipotassium phosphate has the highest VIP score. Manganese sulfate is second with a positive effect also. Ammonium citrate third, but with a negative regression coefficient. High citrate predicts lower A and lower mu. We retrieve then magnesium sulfate with a lower score, but with a positive effect. This exactly matches what we built into the simulation. Dipotassium phosphate and manganese sulfate are the variables with the largest effect on growth. This is exactly the biological mechanism we designed in. Dipotassium phosphate and manganese sulfate supports growth, and citrate inhibits it. The model resolves the contradiction in M4. high dipotassium phosphate and high citrate by correctly identifying the effects of each independently. We run the same analysis with random forest regression. The feature importance plot confirms the sense of each effect, positive for everyone except for citrate. The causal effect analysis go further than PLS and random forest. Instead of measuring statistical association, it estimates the conditional average treatment effect for each variable. What happens to the outcome if you intervene on that variable alone, holding everything else fixed? Manganese sulfate shows the largest causal effect on both param A and param mu. This makes sense when we look at the experimental design. The contrast between M1 and M2, where manganese sulfate is only the variable that's changed from 0.025 to 0.075 gram per liter, gives the algorithm a clean, unconfounded estimate of its effect. By contrast, dipotassium phosphate and magnesium sulfate show near zero effect here. This doesn't mean they are unimportant. PLS and random forest demonstrated they are the strongest predictors. What it means is that in this particular design of 6 media, dipotassium phosphate and magnesium sulfate covary together. They are both high in M3 and both moderate in M5, so the causal algorithm cannot isolate their individual contribution reliably. Ammonium citrate's effect is also near zero, again because its effect is entangled with dipotassium phosphate in M4 and M6. This illustrates an important lesson. Causal inference is only as good as the experimental design supports. When two factors always change together, you cannot estimate their individual causal effect from observational data alone. Enriching the design, for example, adding a media with high dipotassium phosphate and low magnesium sulfate and low citrate would allow the causal algorithm to disentangle this effect. So the causal analysis here gives us a complementary and honest answer. Manganese sulfate is causally validated by the data structure, while the contribution of dipotassium phosphate and magnesium sulfate require a richer experimental design to be causally attributed. The final step is optimization. We set the objectives: maximize param A and maximize param mu. The optimization algorithm searches the medium composition space and returns a Pareto front of optimal solution, combinations that achieve the best possible balance between the two objectives. Every top solution converges on dipotassium phosphate above 3 grams per liter, magnesium sulfate near 0.3 gram per liter, and citrate near 1 gram per liter. In other words, it reconstructs M3 from scratch, starting only from the data. This is a strong validation. Let's summarize what the dashboard found and how perfectly it matches what we encoded in the dataset. M3 is the best medium, with the highest growth rate and the highest final OD, thanks to the combination of high dipotassium phosphate, high magnesium sulfate, and low citrate. We saw that M6 is the worst and that M4 reveals the citrate inhibition. In a real experimental context, this type of analysis will guide the scientist directly to the next experiment. Increase dipotassium phosphate, magnesium sulfate, and manganese sulfate, and finally keep citrate low. Thank you for watching.